In this video, we will discuss about work energy theorem for a variable force. For a variable force in one dimension, we know the work done is given by the formula integration of f dx from xi to xf. Xi is the initial position and xf is the final position. And from work energy theorem, we know the work done is equal to the change in kinetic energy, that is final kinetic energy minus the initial kinetic energy. So we may write the work energy theorem for a variable force like this: kf minus ki, the difference in kinetic energy, is equal to the work done by the variable force, the integration of f dx from xi to xf. So we have to prove it. So let us prove this statement, that is the work energy theorem for a variable force. The kinetic energy in one dimension is given by k equal to half mv square, and the time rate of change of kinetic energy, that is the derivative of k with respect to t, that is equal to derivative of half mv square with respect to t. So half m constant, you can take it outside, that is m by 2, and derivative of v square is 2v into dv by dt, the derivative of velocity with respect to time, and derivative of velocity with respect to time is the acceleration. So it is equal to mass into acceleration into velocity, and from Newton's second law, mass into acceleration is equal to force. So force into velocity. So velocity can be written as rate of change of displacement, that is dx by dt, or derivative of x with respect to t. So you can write dk is equal to f into dx, and integrating both the sides from initial position xi to final position xf, we get integration of dk, that is equal to integration of f dx, and it is dk from ki initial kinetic energy to kf final kinetic energy, and integration of x from initial value xi to final value xf. And if you take the integration of dk, it will be equal to k, and substituting the upper integral minus the lower integral, this side will be kf minus ki, and this side will be equal to f into dx, integration of f dx from xi to xf. So it will be equal to kf minus ki, that is equal to integration f dx from xi to xf. This is what you say work energy theorem for a variable force. So what are the drawbacks of work energy theorem by variable force? It does not incorporate, that is, it does not include the complete dynamical information of Newton's second law. The work energy theorem have no complete dynamical information of Newton's second law, because in Newton's second law, we know it is a relation between acceleration and force at any instant of time. Remember, it is the relation between acceleration and force at any instant of time. But in work energy theorem, it involves an integral over an interval of time. So there is a difference, instant of time and interval of time. That is why you have no knowledge about the complete dynamical information of Newton's second law in work energy theorem. And the second important thing is, Newton's second law in 3 dimension or 2 dimension is a vector form, whereas the work energy theorem is a scalar form which does not contain any direction. So this is the basic difference between the work energy theorem, where we generally we generally take Newton's second law, but we have no complete dynamical information of Newton's second law. Now let us work out a problem. A block of mass 1 kg moving on a horizontal surface with initial speed 2 meter per second, enters a rough patch ranging from x equal to 0.1 meter to x is equal to 2.01 meter. And the retarding force Fr on the block in this range is inversely proportional to x, that is Fr proportional to 1 by x. So Fr is equal to minus k by x, because of it is retarding, so it is minus a constant minus k divided by x, and this retarding force is for the value x lies between 0.1 to 2.01 meter. And if x value is less than 0.1 meter or more than 2.01 meter, the F value, the retarding force value is equal to 0. And here K value is given 0.5 joule. So question is, what is the final kinetic energy of the body? And second question is, what is the final speed of the block as it crosses this patch? So using work energy theorem for variable force, we have Kf minus Ki equal to integration from xi to xf f dx. So final kinetic energy Kf will be equal to Ki plus integration f dx from xi to xf, and that is equal to Ki is half m vi square plus integration of f dx. It is given f value is equal to minus k by x. So minus k by x dx, and value of integration it is given from 0.1 to 2.01. And if you calculate the integration of 1 by x dx, that will be equal to log x to the base e, and value of integration from 0.1 to 2.01. And if you substitute the upper integral minus the lower integral, it will be in the form log m minus log n, and we know log m minus log n is equal to log m by n. So if you put in this formula, it will be equal to log 2 to the power 2.01 divided by 0.1, and here the base of log is e, it is exponential logarithm. And if you convert it into natural logarithm, you have to multiply the value to 2.303, and if you find out the natural logarithm of 20.1, because 2.01 divided by 0.1, that is equal to 20.1, then you will get, and multiplying it with 2.303, you will get the value 1.5. And for m value 1, it is given 1 kg, and vi value is given 2. So if you substitute these values, it will be equal to 2. So final kinetic energy will be equal to 0.5 joule. And in the second question, it is asked to find out the final velocity. The final kinetic energy Kf is equal to half m Vf square. So Vf square will be equal to 2 Kf divided by m. So final velocity will be equal to 2 Kf divided by m square root. If you substitute the value of Kf and m, then you will get the final velocity will be equal to 1 meter per second. So in this video we discuss about the work energy theorem for a variable force, and in the next video we will discuss about the concept of potential energy. Thank you.